To understand the concept of the completeness, we take an example from the Hogg, McCain and Craig's book. Let x1, x2 up to xn be the random sample from the Poisson distribution, and we have to show that y1, that is actually the sum of xi, is a sufficient statistic and is complete. So we have to show that there are two parts in that example. First, we have to show that y1 is a sufficient statistic, and the next step, the next part, we have to show that it is also a complete. So how we proceed that? We have already learned that how we have to show that it is a complete. So we know that the distribution of the Poisson distribution, the PDF of the Poisson distribution, that is theta raised to power x e raised to power minus theta over x factorial and x from 0, 1 up to so on. And we know that theta is greater than 0. So there are many ways to show the sufficient statistic. You can also show the conditional distribution is free from theta. You can also use the giant distribution, and then you can show that by making the factorization theorem. By using the factorization theorem, you can show that one part is without the theta. So first we find the giant distribution. We use the factorization theorem to show that the sufficiency. So the giant distribution is, that is f of xi theta, and that is actually theta raised to power sum x e raised to power minus n theta over xi factorial. And further we can write it into the two parts, that is theta raised to power sum x e raised to power minus n theta into 1 over xi, basically x1 factorial and up to so on xn factorial. So you can easily see that this is a part of h of x theta, and this part is actually the g of x, and this part is free from theta. So we can see that the giant distribution can be written in terms of two parts, one containing the theta and other is independent of theta. So we can say that y1 is a sufficient statistic, and its PDF, its probability mass function is, that is g of y1 theta, can be written as, because it is y1 is actually the sum of xi, so the probability mass function of y1 can be written as n theta raised to power y1 into e raised to power minus n theta over y1 factorial, and y1 ranges from 1, 0, 1 up to so on. So next we find the family of g of y1. So next we consider the family of g of y1 theta, that is theta is greater than 0, and use the condition of completeness. That is the expected value of g of y1, that is equal to 0 for all theta, and this requires that g of y1 be 0, at every point. So that is basically g of 0 that is equal to g of 1 that is equal to g of 2 and that is equal to so on is equal to 0. So 0 basically that is equal to expected value of g of y1, and this can be written as sum y1 is equal to 0 to infinity g of y1 into the probability mass function of y1 that is n theta raised to power y1 into e raised to power minus n theta over y1 factorial. And this can be further simplified as that is e raised to power minus n theta, that is some sort of constant, and the rest of the thing can be written as putting the value of y1 is equal to 0. So that is actually g of 0, and this whole factor is going to 0 plus for the second factor that is actually n theta into g of 1 over 1 factorial. There is no need to write down. The next one is n theta square into g of 2 over 2 factorial plus so on is an infinite series, and infinite series it going to converge to 0 for all theta. Basically we assume that series in terms of theta, and it is going to converge to 0 for all theta. If it is going to converge to 0, then the coefficient must be equal to 0. Then the coefficients must be equal to 0. So that is it, which means that g of 0, g of 1 and up to so on, that all are equal to 0, and that is what we want to prove, and that is what we want to prove, because we have to show that the function basically g of y1 that is actually 0 for all values of y1 y1 up to so on. So we have to show that the function g of y1 is equal to 0 for all y's, and we have to show this. So it means that this is a also complete statistic.